All right, it's time. Welcome back. I am sorry to do this, but I noticed there is a another typo on the old checklist, so I have a new one for you. I'm not sure how this happened, but all semester long, I had just forgotten one of the things. And I didn't notice until now because we're doing it, well, probably won't get to it today, but next time. So you will see there's a new thing, which is number 27 on the list now, which I just did not include, but it's definitely important. So here is yet another version. This will be the last one. No more changes to the rules. If you weren't here last time, I made some big changes to the rules. Good friends. And yesterday, I had appointments with 9 people who came by to do some more of the problems. So keep them coming. You can come by once a week until the end of the semester and try 2 problems at a time. Or 1 if you don't want to do 2 at once. Everybody get a new one of these? All right, sorry to keep on giving you new ones. This is the real deal. So the change is this one has number 27 substitution, which did not appear on the previous lists. I'm not sure why, because I messed it up. All right, great. Anybody got any more questions about those? I think everybody knows what's up by now. All right, let's continue then talking about the antiderivative. By the way, we will be back on our regular homework schedule, so there's an assignment due on Tuesday, and I already posted it. It is unfortunately a little bit long because we're also picking up 1 day from last week, so check it out. Do it early if you can. All right, we're doing the antiderivative. That's what we started with last time. The antiderivative, also known as, this is just sort of another synonym, also known as the indefinite integral. Something like integral of x to the 5 dx. We talked about how to do this last time. This means the antiderivative of x to the 5, which means this is what is some function whose derivative is x to the 5. And the answer is 1 over 6x to the 6 plus c. This is because if you look at the right-hand side here and you take the derivative over here, what happens when you take the derivative? The 6 comes down here, cancels the 1/6, and then turns into a 5, and so you'll get x to the 5. And the c will go away because it's a constant. All right, this is the antiderivative, also known as the indefinite integral. That, what I just wrote here, is a special case of the power rule for the antiderivative, which is super important. And everybody should know this. So this is the general formula for things like that, a power of x. The antiderivative, in order to do the antiderivative, you increase the exponent by 1, and then you divide by the exponent in the front there. This is just like doing the derivative, but backwards. The derivative says you multiply the exponent as a coefficient and then decrease the power. This is the opposite. You increase the power and then divide the coefficient as divide the new power as a coefficient. All right. This rule by itself is nice, but you can also use this inside of a sum or something like that. So if I have something like the integral or the antiderivative of a polynomial, it'd be something like, 3x to the 5 minus 7x to the 4 plus 2x plus 5, something like that. When you have stuff added together, this is what we did at the very end last time, you can just do the integral of each of the little pieces if they're all added together. And the constant coefficients just remain as those same constants coefficients. It's just like when you're taking the derivative. So here I just can go down the line here. The first one, the 3 stays like it is out front, and then the x to the 5, you do the thing which you can still see in the box there. 1 over 6 x to the 6. And then I'll go minus, the 7 stays like it is, x to the 4 becomes 1 over 5 x to the 5. Right? You are increasing the power by 1 each time and then dividing by that new power. Next, 2x becomes 2 times 1/2 x squared plus, what about 5? Anybody recall from last time? What happens when you have just a constant by itself? Yeah, 5x. So I hope you remember what's going on here. This is the integral of a constant. Something like integral of k is just k times x. So in that case, it was 5, and you just get 5 times x. That's because, I mean, this is just a rule that you should sort of remember, but I would say if you're wondering why, I mean, it's because the derivative of 5x is 5. That's the whole point of this procedure here. All right, and then, as always, I go plus c, and that's it. You might want to rewrite this to clean up the coefficients or something, but usually I don't care about that. All right. By the way, when I'm grading the tests, I still see several students who insist on doing ridiculous simplifications after doing the derivative. I would say, I don't want to yuck your yum or anything, but I always say you don't have to simplify. Some people just got to live their truth, I guess. All right, it's fine with me. You're likely to mess it up, though, after you already got the right answer. Then you ruin it by simplifying incorrectly. I would say don't do it, but that's just me. Okay, this is the antiderivative of a polynomial. It's pretty easy. All right, now last time we talked about this rule here, which everybody needs to have that memorized, although you're going to do it so often that I don't think it'll be a problem to memorize. One little caveat about this is it works for every n, works for any n, except there is one value of n for which this does not work, and that is n equals -1. The problem with n equals -1 is if you tried to do this, then you're going to get 1 over -1 plus 1, which is a 1 over 0, and that's not allowed. So let's talk about, what about n equals -1, all right? There is a special rule for this. This is because, I'll just say, you can't do, 1 over n plus 1 to the x, 1 over n plus 1 times x to the n plus 1. This is how you would usually do the antiderivative. You can't do that since it would be, if you really tried that, it would be 1 over 0 x to the 0. If you used that same old formula but with n equals -1, you'd get 0. X to the 0 actually is not a problem, but 1 over 0, this definitely is a problem. All right, that is bogus. You can't do 1 over 0. All right, so if you ever find yourself doing the antiderivatives and you end up writing something like this and you think to yourself, that doesn't look right to me, you are correct. It's not right. You can't do that rule inside the box here. This just doesn't work when n equals -1. So what is the appropriate rule for n equals -1? What is integral x to the -1 dx? This, of course, this would be the same as integral 1 over x, right? That's what x to the -1 means. X to the -1 is the same as 1 over x. We can't use the formula in the box, so we just have to kind of think about this sort of from square one again. What is the antiderivative of 1 over x? Remember what this means. It means I'm looking for some function whose derivative is 1 over x. So is there a function with, derivative of what equals 1 over x, right? That's what we're talking about here. Is there some function whose derivative is 1 over x? Oh, sorry, I'm off the bottom. Any thoughts? Actually, there is. We have in our past talked about a function whose derivative is 1 over x. Anybody recall? Yeah. It is the natural log of x. Remember that? I mean, that was one of those formulas that we had at some point was 1 over x. All right. Oh, can I say one other thing that I've seen on the exams that really kind of puzzled and concerned me? Some people, I write ln x, it appears on the test sometimes. Some people, when they're writing their steps, and I've seen this on a few homeworks also, they write in of x. This is deeply unsettling to me. I mean, I guess you read this L like a capital I, but I ain't never in my life said in of x. I say ln of x all the time. Don't do that. That makes me want to just like throw your paper in the shredder or something. I don't know. This is like, doing it wrong is fine. I kind of take this personally. Like, have I taught you nothing? If you say in of x, I don't mean to get really down on you, but don't say in of x. Come on now. That is not a thing. Anyway, it's this, right? Because the derivative of ln of x equals 1 over x, it means the antiderivative of 1 over x is ln of x. Let me write all this technicalities there. Of course, you always put the plus c. And of course, I put the dx on the left side. Remember, the dx doesn't really mean anything. It's just part of the way we write the antiderivative. 1 over x dx. The integral of 1 over x is ln x plus c. All right, now there's actually another very slight technicality with this. This I'm going to eventually sort of put in a box, but I'm not just yet. That's because this formula, when people write this, I mean, it's fine, and this is true, but the natural log of x, if you recall that it actually doesn't make sense to do the natural log of a negative number. That like, there's no such thing as the logarithm of a negative number. And so what you see on the right-hand side, you can't use negative values for x. But actually, the left-hand side makes complete sense if you use negative values for x. And this is a little weird that you have one function over here for which positive or negative is totally fine. But over here, it must be positive. I mean, the x. The way around this is, if you recall, actually, this is like a sort of actually kind of moment. Actually, the derivative of natural log of absolute value x equals 1 over x. This is an obscure fact that I told you at the time a few weeks ago was an obscure fact, and I said this almost never matters, but there is going to be a time in a few weeks when this is going to matter. This is that time. I don't know if you remember this obscure fact. The log of the absolute value of x equals 1 over x. What's sort of better about this is that in this case, both sides allow the x to be negative, because on the left side, if the x is negative, you immediately do the absolute value, and then it doesn't matter anymore. And so, the sort of proper formula for all of this is usually written in this way, with the absolute values in it. And now this thing, on both sides, the x is allowed to be negative, and there's no problem with negative x's. All right, so when you do the antiderivative of 1 over x, we will say it's the natural log of the absolute value of x. All right? These are vertical bars here, absolute value bars, all right? Don't say ln of ixi. Nobody has ever said that. Was there anyone out there who thought those were capital I's, even though I said absolute value every time? I never said ixi. No, nobody would ever do that. All right, enough of that. Okay, this is the formula for the integral of 1 over x. And I will just remind you, this 1 over x, of course, is the same as x to the minus 1. So you use this formula when you see x to the minus 1 or 1 over x. Those are the same thing, just written in two different ways. But in any case, the answer either way is natural log of x. Natural log absolute value of x plus c. All right. This is, so this is the other part of the formula to remember about powers of x. If it's x to the n, you do 1 over n plus 1, x to the n plus 1. Except if the n is negative 1, then you do natural log of absolute value of x. All right? So what we've talked about, over the next few times, we're going to be talking about how do you take the integral of various more and more complicated things. So we already know how to do a polynomial. In terms of the derivative, when you do more and more complicated things, you learn things like the product rule, the quotient rule, the chain rule. We don't really have rules like that for the indefinite integral, at least not ones that we're going to get to in this class. But there are some simple tricks. So I'm going to say other tricks for the antiderivative. The big problem is if you have a product on the inside, if there's multiplication, if there's a product, this needs some tricks. All right, for example, if I had something like integral of x times x squared plus 3, it is not correct to just separately do each of those two things on the inside. You might say, oh, can I just do like x gives me 1/2 x squared, and this gives me 1/3 x cubed, and this gives me 3x, right? Can I just do that? The answer is no. This is not allowed. Because of multiplication, there are special things that you have to do, special tricks that are required. Just like when you're doing the derivative, if there's multiplication, you need to do the product rule. You can't just take the derivative of each part. So do not just do the integral of each part separately. When there's multiplication, we need to somehow handle the multiplication before doing the integral. So you need to handle the product before doing the integral. And this is true of quotients also. If you see a quotient in there, you can't just do the integral on the top and also on the bottom. You have to somehow handle it before doing the integral. All right, anybody see what, in this, we can actually do this example with a fairly simple trick. What should we do? Anybody have an idea? How would I handle the product before doing the integral? The product is multiplication right there. Any thoughts? Handle it. Got an idea? Yeah? Yeah, you can just like actually multiply it by distributing the x here. So I'm going to sort of, this is not really a real trick with a name. I'll just say multiply it out, right? So this thing here becomes integral. I'm just going to distribute the multiplication in there. I'm not doing the antiderivative yet, so I'm still going to write the integral sign. But now it says x cubed plus 3x, right? I distributed the x. Like this. I know some people like to draw the little arrows. Them's the little arrows. All right? I'm not done yet. This is not the antiderivative yet. I just rewrote the inside. Now I'm actually going to do the antiderivative. And I do the rule with the, the exponent. So x cubed becomes 1/4 x to the 4 plus 3x becomes 3 times 1/2 x squared. And then I go plus c as always. All right? So multiply it out. This is how you should handle products inside the integral. You have to actually do the multiplication first and then do the integral. All right, let's try another one. This one looks a little different, but it's a very simple, a very similar sort of thing we have to do here. 2x plus 1 squared. Now this one is not written like a product, it's written like a, like a power, like an exponent there. But we can do the same kind of a thing here. How would we multiply it out? Well, in this case, to multiply this out, you would write two of those things next to each other and then do the FOIL. So this is what I'm going to do for this one. I'm going to think of this as multiplication. 2x plus 1, 2x plus 1, like that. dx, of course. And then do the FOIL there. You better write this integral sign every time because these steps are just re-simplifying the inside. I'm not actually doing the integral yet. So make sure you keep on writing the integral sign. Okay, doing the FOIL now. I go, the first thing is 2x times 2x is 4x squared. On the outside, I get 2x times 1, that's 2x. In the inside, I get 1 times 2x, another 2x. And at the end, I get 1 times 1, which is 1. All right, so that's the FOIL. That's what I did in that step. And now that it looks like a polynomial, we just do the integral term by term, right? This is legal because they are added. This is the whole thing. When they're added, you can just go one at a time. When they're multiplied, you got problems. You got to deal with it somehow. But This one, I go 4/3 x cubed, right? Would you mind? Sometimes I'm going to write, instead of 4 times 1/3 x cubed, that's the same as 4/3 x cubed. I hope you don't mind. And then 2x gives me x squared. 2x gives me another x squared. And then 1. What do I do with 1? 1 gives you just x, right? Because remember, if it's just a constant, it becomes that same constant times x. And this is 1 is a constant. It's 1 times x. All right, there you go. This is how it goes. All right, I got one more like this, and then I have some for you all to try. How about this one? Looks like a quotient. I will say again, you should not just do the integrals on the top and also on the bottom. You can't do it that way. Because it's a quotient, you have to somehow deal with this as a quotient. I would say that there's a few ways that you could think about simplifying this. To me, the easiest way to write this out would be rewrite the bottom as a negative exponent. So it's because I like multiplying better than dividing, I'm going to convert this into a multiplication. So dividing by x squared is the same as multiplying times x to the minus 2, because that's what x to the minus 2 means. It means x squared in the denominator. All right? And then from there, I can distribute, right? I distribute like this. So still not doing the integral yet, but I'm distributing. Can anybody say what's x times x to the minus 2? When you're multiplying powers like this, you should think of adding the exponents, all right? So this is x to the 1 times x to the negative 2. You add the exponents, I get x to the negative 1, right? And then the second one, 1 times x to the minus 2, that's just x to the minus 2. All right? And now I converted it into stuff which is only added, and so we can just do the integrals of each one of them. So I go x to the minus 1, what's the integral of that? Shout it out if you like. What is it?
Oh wait, that's wrong. 1 over x.
X to the minus 1 is the same as 1 over x. I want to know what's the antiderivative of that. Yes, she said ln absolute value of x. That was the thing that we just talked about a few minutes ago. Plus x to the minus 2. This one, you do the usual power trick, which is to say you increase the power by 1. So minus 2 becomes negative 1 now, and then you divide by that in front. So it's like that. And then, of course, I put the plus c. You always put the plus c at the end, which is a bit of a nuisance. It's usually not relevant. In a problem like this, it really doesn't matter at all, although it's not technically correct unless you put it there. All right. Great. Let's do some. I got some for you all to try. See what you think of these. The first one is easy. You just directly do the thing with the powers. The other ones, you'll have to think a little bit about how you're going to handle the weird stuff on the inside. And there I used a T just for fun. All right, see what you think.
coefficient just stays, so that this 8 just stays at the 8. And then you do the power. Okay. Good. Yes. Okay. This is good so far. Sounds good here? Yep. All right. This, does appear as part of the answer.
Oh, because it's not the
Yeah, it's just the here. X, that's great. This becomes 1.
Oh,
X
I'm
to the 0
thinking-
is 1. Yeah, so here you put 1, and then the next step is when you do the integral.
So this would be x.
No, just 1. Like this x really is x to the 1. And when you multiply, you add the x1s, it becomes x to the power 0, which equals 1. Because then you
Oh,
to the 0.
so then this would just go. Thank you.
And then the next step is when well, actually, this one is
Thank you.
I'm good here? Yeah, now I'm going to distribute. Yeah, I mean, nothing really weird happens. It's just going to be 3 times x on this one. For the first part. So this is right, but you should put the plus c. I'm good here? You have, this is great, but you wrote the integral sign too much. The integral means I'm going to count this derivative. That, this step we did means right, you should know. Okay. This is okay here? Alright. I suggest, yeah, this would need to be this is not quite right. Multiplication of x times x. Okay. Well, this is good. That's good. I think so. Yeah, this is great. Okay here. Yeah, this is good. This 4 turn into x. Which is the working. You have a constant that becomes that same constant times x. So actually, this is and one last. Do it right. The integral here, you should not. There shouldn't be an integral. Because this is the step in which you actually did it. That's the answer. Yeah. Whereas here, you keep the integral because here all you did was simplify the inside.
Yes.
So what about right here? Should be you have to think like in that step, were you just re-simplifying the inside, or did you actually do it? Yeah, because you didn't actually. Yeah. Yeah. Still good? Okay. That's
Oh, so it's not.
I think you just heard.
Think about x and other things to find out one. Whenever you use that full value, you simplify one.
You did? Was it like actually taking it back? You just gave it the.
It's like what happened with all of a sudden, the heat just goes in front and then x is 2. And the next one is -7.
Oh, okay, so.
Like a lot?
Yeah, you said a lot. So
You get something that looks like this. But it's not.
All right, let's talk about these. I know some people are done, some people are not. That's okay. Okay, let's try. The first one is the easiest. Actually, I forgot the dx. Nobody complained about that. Technically, it should have the dx there, although it doesn't really have meaning by itself. But anyway, the coefficients stay like they are. I think everybody got this one as I was walking around. 7 and then 1/2 x squared, and then the 3, remember, just a constant by itself becomes that same constant times x. So it's like that, and then of course you got to put the plus c at the end. All right, I think pretty much everybody got that one just fine. The second one, t plus 2, the whole thing squared. This one you have to simplify yourself, which I will do by multiplying on the inside, doing the FOIL, right? This is t plus 2 dt. This is t squared plus 2t in the middle plus 2t plus 4 dt. And now I will do the antiderivative. Notice I still wrote the integral sign in each step here. That's because in those steps, all I was doing was rewriting the inside. I wasn't actually doing any antiderivative. Now is the time when I actually do the antiderivative. It's 1/3 t cubed plus a t squared plus another t squared plus 4t plus c. The 4, remember, a constant by itself. I usually say becomes that same constant times x, although it's not always x. Here the variable is called t, so you should write t, not x. All right. Any questions about that? Excellent. Let's try this one here, 3 minus x over x. I'll do this one later. This one, as I was walking around, I saw, you should resimplify this or rewrite the inside so that it looks like a product using a negative exponent. So this is just like an example that I did a moment ago. Rewrite this so that instead of a quotient, which I don't really like, it looks like a product, which is a little nicer, and then I can distribute the product. So I'm going to distribute here and here. When we distribute, 3 times x to the minus 1 is 3x to the minus 1. You can't do much with that. And then it's a minus. Here I have x times x to the minus 1. I saw a lot of people as I walked around puzzled about how do I do x times x to the minus 1? Well, remember, you are adding exponents. So this is like x to the 1. This is like x to the minus 1. When you multiply those, you add the exponents, you get x to the power 0, and which is 1, right? Anything to the power 0 is 1. Another way of thinking this through is this is just x. X to the minus 1 is 1 over x. So when you multiply x times 1 over x, you get 1. They cancel. Anyway, this is 1, however you want to think about that. All right? Again, I still wrote the integral sign because in that step, all I was doing was simplifying the inside. And now, finally, you actually do the integral. So 3x to the minus 1 becomes 3 natural log absolute value x. That's the special rule for x to the minus 1, remember? And then minus 1 becomes minus x, because that's a constant. And a constant becomes that constant times x. It was the constant 1. And then plus c, of course. Don't forget the plus c. Any questions about that? All right, and the last one. The last one. I don't know if this one's easier than the previous one. I don't know. I would say, again, rewrite this using negative exponents because I don't like the little fractions. I don't like these little quotients here. Rewrite using negative exponents. So actually, the first one is fine like it is. 3 over x squared. Anybody, what did you do to rewrite this using a negative exponent? I know some of you did it. 3 over x squared.
3 times x to the negative 2.
3 times x to the negative 2. Great. And then 1 over 5x. Again, rewrite this using a negative exponent. I have x in the denominator, so when I bring that upstairs, it becomes x to the minus 1. It should be this, 1/5 x to the minus 1. This actually is a little tricky. Make sure that you don't, can I just say, this is not 5x to the negative 1. Those, of course, are different, right? 1/5 is not the same as 5. So there's a difference. Why did I use 1/5 rather than 5? It's because the 5 is in the denominator, right? When you sort of bring x out of the denominator, it becomes x to the minus 1. But you don't, I mean, the 5 doesn't come out of the denominator unless you also wrote 5 to the negative 1, which is okay, I guess, but that's the same as 1/5. There's no reason to write it outside of the denominator. Definitely don't change it into a 5. That is quite different. Oops. All right, anyway, continuing. We're not done yet. Now we actually do the antiderivative in each of those 3 terms. We get 75 times 1/3 x cubed plus 3x, so 3 stays like it is. X to the minus 2, I increase the power by 1, it becomes x to the minus 1. And then 1 over that, so it's 1 over minus 1, x to the minus 1. Minus 1/5 x to the minus 1. Again, we use the special rule for x to the minus 1, which is the natural log. So this is 1/5 ln absolute value x. There you go. These are simple tricks for the antiderivative. We are going to learn some more sophisticated tricks, but these ones are just about sort of simplifying before doing the integral. All right. Anybody got thoughts about these? All right, excellent. Let's do just a little more simple integral tricks. These are not really tricks, but how about integral of exponential functions? Integral of exponential functions. We can do the integral of exponential functions. I'm talking about stuff like e to the x or like 2 to the x or something like that. The integral formulas for those are fairly simple because they have such simple derivative formulas. For instance, we all know, everybody remembers, derivative of e to the x is e to the x. So what is the antiderivative of e to the x? Well, it's the same thing again, right? When you take the derivative of e to the x, the answer is e to the x. That means if I ask you to do it backwards, you again just get the same thing again, right? The derivative of e to the x is e to the x, which means the antiderivative of e to the x is e to the x, plus c, of course. There was also, just because this comes up often, what if you had the derivative of e to the kx? So there was an extra constant inside the exponent. This, if you were using your derivative rules properly, like this could have been one of our test questions last time around. The derivative of that, the derivative of any e thing means you get the same thing again, but then you should multiply times the derivative of the inside of the exponent, which in that case would be k, the constant, because kx, the derivative of kx is just k. That's from the chain rule, that times k. All right. But anyway, what this rule says is when you take the derivative of e to the kx, you get the same thing again, but you have to multiply times k. And that means the antiderivative, doing the opposite, it means you get the same thing again, but you got to divide by k. It's just the same rule, but sort of the other way around. So I'm going to write this like e to the kx is 1 over k e to the kx plus c. This is the antiderivative of e to some power with an extra constant in there. All right? So these are the rules with e's, and things tend to be a little bit easier if it's an e because you don't have to deal with other nonsense. But there are also rules with other numbers for the base, a to the x. Anybody actually remember this formula? Derivative of a to the x? It is a to the x times ln a is the formula. Yeah. So that was one of our old formulas. It says when you take the derivative of a to the x, you get the same thing, but you got to multiply times ln a. The antiderivative is the other way around. It will say you get the same thing, but you got to divide by ln a. So the integral formula for that, a to the x dx is 1 over ln a to the x, plus c, of course, as always. All right. And then I got one more. There's kind of a combination of these things. What if you also had an extra constant up there, a to the kx? This is the fanciest of all. It would look like a to the x ln a times k because of the chain rule you multiply times k. And so that one, doing the derivative, you multiply by k and ln a. Doing the antiderivative, you should divide by those things. So this is the most complicated of these. It says 1 over k ln a to the kx plus c. So these ones here are the formulas for integrals of exponential functions that we're going to use. All right. They are the same formulas as the derivative formulas, but they're just sort of backwards in the sense that you are dividing. For the antiderivative, you got to divide by these things rather than multiplying, which is what you do for the integral. So for the derivative, you would have multiplied. For the antiderivative, you instead divide. All right, let's do a few quick examples, and I have a few quickies of these for you, and then we'll go on to something really completely different. Not completely, but slightly different. All right, can we remember these formulas? Sorry, I got to scroll them. Let's just do some examples here. How about 7 e to the 3t dt? I'm using t's. I hope you don't mind. All right, what's it going to be? Well, we need to use, one of these formulas that I wrote up here. First of all, this is an e, so I'm going to use one of the ones with an e in it. What about the 7 out front? Actually, those formulas that I just said, have no room for a number out front. That's because when you're doing the antiderivative, a coefficient in front is just going to stay like it is. This is just like all the examples that we just did a moment ago. So in my answer, it just begins with the 7 in the front. The coefficient always just sort of carries over exactly as it already was. And now I have to do the integral of e to the 3t, and for that I'm going to use this rule here, this e to the kx thing, where the k is 3. And so the answer is going to say 1 over 3 e to the 3t. So this is 1 over 3 e to the 3t plus c. All right? So this was the e to the kx rule. And also just leaving the 7 as a coefficient in the front. All right. That was a simple one in my opinion. Let's try, so I have just a couple more simple variations. How about integral of 2 to the minus 2x dx? All right. So the first thing you should do is see this and realize that this is an exponential function because there's x inside of the exponent, all right? That means you're not going to do one of the ordinary power rules where you increase by 1 and whatever. You don't do that because the x is inside of the exponent. You have to use one of these rules up here. Which one is it going to be? You see them both at once? Which one is it? Well, I can say, first of all, it's not either of these with the e's because there's no e down here, right? The base of this exponent is not e, it's 2 instead. That means I'm going to have to use one of these because these are the ones you use with a different base other than e. And I think it's the second one just because I have this extra number up here, all right? So I'm going to use this formula here. So I will say parenthetically here, this is the integral a to the kx rule, where a in my example is 2 and k is -2, right? A is the big number down there, and then the k is the coefficient inside the exponent. But other than that, I just plug it all in. So I'm going to get 1 over -2 ln 2 times 2 to the minus 2x. Just plugging into the last of those formulas in the box there. All right. And I got one more, and then I have some for you all. I got my one more here. How about e to the 3u? Sometimes I like to change around the variable names. E to the 3u plus 7u to the 2. All right? Now, this is two things added together. So first of all, you should realize I'm just going to do each of them separately. All right? Because they're added, you can do that. I'll just do each of them separately. E to the 3u, you use the e to the kx rule. It says 1 over k e to the kx. That's what the answer should be. So this one becomes 1 over 3 e to the 3u. That was the e to the kx rule, which I've scrolled by now. And then what about 7u squared? This one is actually quite different. Anybody, this is perhaps a bit of a trick question. I don't know, it's not really a trick question, but how do you handle u squared, 7u squared? Yeah?
Be 7 times 1/3 u to the 3rd.
Yeah, right. This actually is not one of these exponential functions at all. So this will be part of, your job on the test or whatever, is to, recognize which of all of these rules is appropriate to use here. In this case, the variable is not inside of the exponent. So this actually is not any of the ones that I just put in that box there. Those are all about exponential functions where the variable is inside the exponent. But in this case, the variable is down here. In that case, you just use the ordinary power rule for the integral. It's like that. All right? That's how it's done. I got a few of these for you all to try. And then we'll talk about something new and different. So the first couple are pretty straightforward. The next ones you'll have to do some thinking. So the first two are fairly easy. The second two you'll have to think about resimplifying the inside before doing the integral. I am sure you can handle it. All right. Bend over. Look at it while it's doing. Excellent mentor. Role model. How's it going?
sit up to that. This, it's just this one that I did with.
Yeah. Oh, so you just.
This being a constant coefficient just stays as a coefficient, and that's what they use.
Okay, so it's like the simple.
Yeah, that first one. Okay. Yeah, because we add the exponents. All right.
Would this be?
This is good so far. Yeah, you're using the a to the kx for this. Yeah, that's good. The real issue is actually nice.
Oh, right.
This power to do some simplification. So it's rational.
Okay, yeah, I did. Thank you.
How's it going? Yeah, this looks good. Yeah, good.
That's right.
There should be this. Yeah, we multiply these, you add the exponents, so it's 4x plus 4x. Still good here? Yeah. Yeah, this two out here is it's serious. You have to do it. So in this case, if it were the derivative, you would do the chain rule, but for the antiderivative, you would do some other simpler tricks, which in this case would be just multiply out.
Oh.
Two of them. How's it going? Okay. So this one you use the formula for e to the kx. This one is like that this time.
She's gonna be so worried. No, I told her that we put it back on.
So there's two things I need to do.
Like that.
Here.
Yeah. So white is like
This 7 here.
You probably could rub one.
you see the leg?
Yeah.
Absolutely. It's like that did you believe it?
Yeah.
Oh,
She's gonna turn the car.
come on. Come on.
No
It should be.
That wasn't this time.
Just like that.
Yeah. It's not as believable since the first one.
Yeah.
But like, she's so lazy. We talk about her all the time. We always say we're gonna get she wants me to It's so funny.
Still good here? Maybe that's good. Just drinking it.
I know.
Is this?
She's got to learn
Right.
right.
Not quite. Where'd you get these guys? From the formula?
Yeah, it's right. That's what I did.
Yes, there's more of it though. So what actually is giving you 5 minutes with it?
Oh, you should just look like that.
It's this rule you're using, which has this fraction thing, and there's this seconds.
Okay. Okay.
Doing good here? Yeah, I think so.
That's great.
Yes, this is weird. Let's see. It's not wrong.
Do I have to put another plus C?
No.
So if this one now.
Oh, you did 2 plus 6.
Yeah. So
Yeah.
it's only at the top?
Yeah, it's just because the plus C represents
Of any
any
constant.
number, yeah, so writing it twice doesn't really. Okay?
Probably.
This is the right strategy, yeah. Now you should do the 4 here.
Okay.
You didn't like that, I guess? Just remember to add the exponents. Oh, this, and this 4, it should be 4x.
Oh, okay.
What's going here? Distributing? Yeah, that's great. Mhm. Yeah, this is not quite right. Each of the 5x is 1
Oh,
this one.
yeah, this
Okay.
one.
But this is the derivative. We should actually not touch the
that's why.
All right, can we chat about this? Okay, so the first one is very straightforward, plugging into the formula. The 2 stays as a coefficient, and then you use the e to the kx formula. E to the 5x gives me 1 over k e to the kx, which is 1 over 5 e to the 5x, and then plus c. So that was just this directly plug into the formula. And then this one over here, similar, you just directly plug into the formula. This time you need the a to the kx formulas. This one you should get 1 over 2 ln 7, 7 to the 2x, plus 1 over 3 ln 4, 4 to the 3x. That was using the a to the kx formula twice. Just directly plugging in. No funny business. All right, now this one, 2 plus this one over here, this one does require some funny business, and it's really because of this exponent here that really messes it up. So I'm going to multiply out the binomial squared doing the FOIL thing. So this is 2 plus e to the 4x, 2 plus e to the 4x again, dx, right? And now we do the FOIL by distributing everything. It becomes 2 times 2 is 4. On the inside, I get 2 e to the 4x. On the outside, I get another 2 e to the 4x. And on the end, I get e to the 4x times e to the 4x, which all good boys and girls remember, you add the exponents in this situation. So e to the 4x times e to the 4x, we add the exponents, we get e to the 8x. I hope you did that properly. But anyway, now that they're all added together, we can just go down the line and take the antiderivative each time. So the 4 becomes 4 times x, because that's what happens with just a constant. The next one becomes 2 times 1/4 e to the 4x. That's the e to the kx rule. And then the next one is the same, 2 times 1/4 e to the 4x. And then finally, the end, e to the 8x is 1/8 e to the 8x. That's, again, the e to the kx rule. I hope you got some like that. Anybody got questions about that? If you like, you can simplify more, but I don't like. All right, and then the last one here. This one may be a little easier. I don't know. This one, again, you have multiplication inside, which you need to do before taking the integral. So I'm going to distribute here, like so and so. So it's going to be 3e to the x is the first one, and then minus e to the 5x. Remember, you add the exponents in this scenario. So e to the x times e to the 4x, you add them up. X plus 4x is 5x. All right, and now we do the integral each time. 3e to the x, the 3 is a coefficient, and so I just get 3e to the x again, and then minus e to the 5x. This is the e to the kx thing again, 1 over 5 e to the 5x. That's what it is. Any thoughts or concerns about those? All right, great. We got a little more than 10 minutes left. I think we can get started on the next thing. We'll just do maybe an easy one from the next section. All right. Actually, this is the same section in the book, I believe, but I broke it out on our list of topics into, this is going to be number 26. So number 25 is just called the indefinite integral, and that's what we just did. The next topic is number 26, which is called initial value problems. Initial value problems. This is, I would say, a more easily rememberable, or what this is about. This is about solving for the plus c. The plus c, which I've described as just sort of like a nuisance this whole time, you just have to remember it. There are some cases when the plus c actually matters for something, and that is usually in the context of this things, what we call initial value problems, which are actually very useful in the real world, although we won't get to any applications today. But next time we'll do some real world sort of applied initial value problems. But anyway, as we all know, the antiderivative always produces some kind of extra plus c, right? This is a simple example. The integral of 3x squared dx is x cubed plus c. And the reason we do this, we need this in order for it to be correct, since the derivative of x cubed plus c always equals 3x squared. I will say no matter what c is. And the c really could be any constant. And there is no way to, I said initial value problems is all about solving for the c, like actually figure out what the c is. But in a problem like this, there is no specific value for c. It can be any constant. And so without, I will say it this way, without more information, we can't know what the c is. Like what number it is. It can be any number, and it really could be anything. There's no way of telling what specific value the c is without more information. If I do give you some more information, though, then you can often solve for c. So if we're given more information, info, we can actually solve for the c. And here's an example of that. So here's typical initial value problem. Will look something like this. I would like to find f of x so that f prime of x equals 2 to the power 3x and f of 0 equals 10. All right? Find f of x so that f prime of x is 2 to the 3x and f of 0 equals 10. So here there's kind of two things that I sort of said. The first thing is this. Another way of writing this is f of x is the antiderivative of 2 to the 3x dx, right? This, it says the derivative, this is a f prime. Make sure you wrote down that prime. This says the derivative of f is that. Writing this the other way around, it means f is the antiderivative of that, all right? And then this right here, the other part, f of 0 equals 10, this is referred to as the initial value. All right, so this problem here is about finding what the f is. Now, when you do this integral, you're going to end up with the plus c, which ordinarily we have no way of knowing what the extra plus c, the constant, is. But if they also tell you the initial value, you can use this to solve for the c at the end. All right, so this is what we're going to try to do. And I mean, it's not very complicated. Find a function so that its derivative is 2 to the 3x, and also this is true. So how we're going to proceed, the initial value, I will just say, this is used at the end to solve for the c. right? You don't, it doesn't matter until the end of the problem, but you're going to use that eventually to solve for the c after doing the integral of something or other. All right? So first of all, we have f prime of x is 2 to the power 3x. So that means f of x is the antiderivative of that. Right? Because this says the derivative of f is this. To write that the other way around, in terms of antiderivatives, it means f itself is the antiderivative of this. Because that's what it means when I say the derivative of f is 2 to the 3x. All right, anyway, do the integral now. This is just one of those formulas that we just talked about. It's the a to the kx one, where a is 2 and k is 3. So this looks like 1 over 3 ln 2, 2 to the 3x plus c. All right, this is f of x. Now this is not, sorry, I'm off the bottom. This is not quite my final answer because I didn't do the second, this thing, right? I'm going to use the initial value at the end to solve for the c. So this is generally, this is sort of halfway there to my answer. Your job in this case is to find f of x. Now I found this, but I still have this unknown constant in there. So I'm going to say now we use the initial value, which is f of 0 equals 10. To solve for c. All right? And how do we do that? Well, when it says f of 0 equals 10, what that means is you plug in x equals 0 and then set it all equal to 10. So I say 10 equals 1 over 3 ln 2, 2 to the power 3 times 0 plus c. I plugged in x equals 0, and that whole thing has to equal 10. That's what it means when it says f of 0 equals 10. It means if you use x equals 0, the whole thing's going to equal 10. So that's what I do. Plug x equals 0, set the whole thing equal to 10. And this, in theory, you should be able to solve for c, right? Because everything else here is just numbers. So move the numbers around however you need to in order to solve for c. Now I can kind of simplify here. What is 2 to the 3 times 0? Show me the fingers if you like. It is 1. Anything to the power 0 is 1. Everybody knows that. So this 3 times 0, of course, is 0. So this is 2 to the 0, which is 1. So that's just 1 over 3 ln 2 plus c, right? And I can solve for c by subtracting, I guess. Subtract 1 over 3 ln 2. So c is 10 minus 1 over 3 ln 2. And that, ordinarily, I wouldn't give you a weird number like this, but I put this into my calculator ahead of time. I got 9.52. That's what the c is, apparently. All right? And so now we're done with all the work here, but just to say the answer. The final answer, remember what the question was find f of x that has this or that property. F of x is here. This is how I wrote it with the c, but now I know what the value of c is. So I'm going to write that same formula again. 1 over 3 ln 2, 1 over 3 ln 2, 2 to the 3x. Instead of, I'm just copying here, but now instead of plus c, I know what the c is. It's 9.52. This is my answer. All right? So you can solve for the plus c if you are also given the initial value. That's why these are called initial value problems. It's that thing where you solve for the plus c. All right, I think that'll do us for today. We'll do more initial value problems next time.